Hello, and welcome to this webinar, Teaching Physics with MATLAB, Simulations and Experiments. My name is Lopez del Puerto. I'm an assistant professor of physics at the University of St. Thomas in St. Paul, Minnesota. Most physics research these days involves the use of computers. We use them for everything from data collection and analysis to simulations, symbolic manipulation, and of course numerical analysis as well. The AAPT came out with a rationale for their statement on computational physics, and it reads, "Computational physics has become a third way of doing physics and complements traditional modes of theoretical and experimental physics." So we know that we need to include computational physics into our curriculum, but the questions then become, what should we include, and how should we include it, and in a packed curriculum, where should we include it? The physics curriculum is rather extensive, and finding a place for computation can be a challenge. In 2006, Computing in Science and Engineering magazine actually commissioned a national survey where they asked undergraduate physics programs to provide a snapshot of their computational practices in physics courses. What this survey found was that out of 167 physics departments that responded, 55% of them had a separate computational physics course. 29% had embedded computational activities in traditional physics courses. And of this 29%, departments could be doing as little as one faculty member introducing computation in his or her course, just as in an ad hoc basis, or it could be as much as the entire department systematically embedding computation into most or all of their physics courses. This latter approach is what we have actually taken at the University of St. Thomas, and that is exactly what I will describe today. And I'm going to concentrate on the sophomore level applications of modern physics course and laboratory that actually serves as an introduction to computational physics at St. Thomas. After a 2002 internal program review of our physics department, it became clear that the characteristic that differentiated our strong and weak students was their ability to apply analytic, computational, or experimental skills as necessary, and also to effectively communicate those results. We want all of our students to have those skills, and while the first was already a strong part of our curriculum, the analytic skills, and adding communication was pretty straightforward, embedding computation and experimentation throughout the curriculum actually required significant reform. Some of that reform is described in the reference showed at the bottom of this slide, and some of that reform is still ongoing. This is a snapshot of our Physics BS program. And as you can see here, all courses 200 level and above actually include computation in varying degree. So the colored letters are meant to show emphasis on different aspects of the course, either theory, experiment, computation, or writing communication skills. So as you can see, all of the courses 200 level and above actually include some computation. Before the past couple of years, we actually allowed students to pick the language of their choice for the computation that was required in the different courses because there was no common language for all of the students. This made it difficult for the instructor to teach programming techniques and even for students to work collaboratively because they were often using different languages and were not able to translate between one language and the other. However, when we began redeveloping the applications of modern physics course and laboratory in 2008, which is a required course for all physics and electrical engineering majors, that gave us a chance to focus the laboratory on computer simulation and to have a common base for all of our students to be proficient in a particular computer language, and we chose MATLAB for that. And this tool that we have now given to our students, all of our students, we can then use in our upper level courses. So allow me to reorganize this diagram such that you see that the computational skills acquired in the applications of modern physics course really serve as the base of our computational curriculum. So this is the broad and common base that all of our courses build on. And I haven't addressed the question of why we chose MATLAB, but we chose it because it is a high-level computer language that is widely used in both scientific and engineering applications. And remember that this Applications of Modern Physics course is required of both our physics and engineering students. But also MATLAB is an in-demand skill in the job market, and so this is already giving our students additional skills that are marketable. Now you may have noticed from previous slides that our modern physics is perhaps a little different than at other universities in that we have two courses that relate to modern physics, and they are in fact order independent. Foundations of Modern Physics includes relativity, cosmology, and particle theory, and the main focus of its laboratory is to develop experimental skills, hence the larger font E in that course, while Applications of Modern Physics, on the other hand, which includes topics from a material science perspective, that is, building from properties of single atoms to collections of atoms. So we go through quantum dots and other nanoscale systems, and then on to solids, with applications interwoven throughout. That laboratory is the one that focuses on computation. So our physics majors take both courses, and in that way gain both experimental and computational skills. Our electrical engineering majors only take the Applications of Modern Physics course, which includes somewhat more computation and less experimentation, but they get those skills in later courses. So what do we do in the laboratory for Applications of Modern Physics? Well, what we try to do is connect the theory and all of the idealized physical systems that we present in lecture with real systems, and we do this through the use of computer simulation and validation experiments. We use simulations that are already written, and most of those come from the Physics Education and Technology project from the University of Colorado. And we also use simulations that the students write themselves in MATLAB. A majority of the students are electrical engineering majors, that's the bigger population, and they do have often some experience with MATLAB, but in fact we don't require any prior experience in this course, so we do start from the beginning. The unifying theme for the laboratory is the particle in the box, which we explore from the classical to the quantum level, and from one particle to many particles. And each laboratory that I will talk about today includes a computational and an experimental component, and they're each 1 to 2 weeks in length. So we begin the course by introducing computation and introducing the idea of using computation in physics. We actually start with classical statistics, and so we talk about how do we apply statistics to physics and how we can use MATLAB and simulations to gather data that can help our understanding of statistics in physics. We find that through writing a simulation, students actually gain a deeper understanding of the physics that is involved. Simulations encourage creativity and experimentation with the code, as there are many ways in which to solve the same problem. And they allow us to ask more open-ended questions, which is really a challenge to the students and encourages collaboration between students, but also pushes the students that are familiar with MATLAB or maybe more knowledgeable about physics to really explore the limits of the simulations. We do expect all students to complete certain tasks, but we pose additional questions to challenge those more advanced students. Now what you're watching in this short video is one of the simplest simulations that we have, and I find that it is a great way to introduce students to MATLAB. It's just a particle moving classically in a box, being reflected off of the boundaries following dynamics. And it really does teach students what a simulation is, and it refreshes and deepens their understanding of introductory classical mechanics. What you see on the right is a little tracker for the statistics of this particle, basically counting how many time steps the particle spends at each particular x position. And so then we can ask questions about how much time the particle spends on the left versus the right side of the box, for example, to check that our simulation actually corresponds to what we would expect from our knowledge of physics. Now, what are the goals of this lab? Well, the first one, which is the conceptual goal is to develop familiarity in applying statistics to classical physics, and that's really the connection with the lecture part of the course. The modeling goal is to develop an understanding of how this model is developed and implemented. And the computational goal is to introduce MATLAB and for loops, if statements, and basic plotting, which is all that you saw in that previous slide. Now what we do after that is that we have our students track statistics for the particle, like I said, time spent on the left versus the right half of the box, for example. They understand how to discretize an equation. They decide on appropriate time steps and how long to run their model in order to get adequate data. Now for this first exercise that we do in the laboratory, we do give them a sample code that they start from. They have to understand what the code is doing in order to modify it and do the lab. And many of the future labs are actually modifications to this code. So this is a way to introduce them to MATLAB that is a little less threatening than starting with a blank screen. Some other questions that we may ask is, what happens if you change the time step and make it either too big or too small? How do you choose a particular time step that you used in your simulation? And they have to provide an explanation for that. And then actually track the statistics and see whether their predictions agree with their data, and if not, why not? The next couple of weeks in lab are actually spent studying a two-step system, which is just a little above what we just did, and they do both an experiment and a simulation. So what you see on the bottom is the simulation, where the upper level is on the left, the lower level is on the right, and so as the particle bounces around, if it doesn't have enough energy, then it will not be allowed to go into the upper level, and the particle gets a random kick every so often. What you see on the top is the experiment, where the random kicks are provided by squiggle balls that are motorized, and the particle moving around is that yellow ping pong ball. And so students use a chess clock to track how much time the ping pong ball spends on the upper level versus the lower level. And they can then compare their simulation to their experiment. The next few labs that we have been developing in the past year is a laser lab, where students study how a laser works, and we do this first through a PhET simulation and some of the materials that the University of Colorado has developed and that are available online. We've modified them for our purposes so that the students work through the theory at the beginning part of the lab, and then we have them predict spectral output of a laser, the non-lasing light on the side of a clear case laser, which you can see on the picture there. And so what they do is they take data files from helium and neon known energy levels that are available through the National Institute of Standards and Technology, and they read those files into MATLAB and process the data in order to show the spectra that you see there on the screen, and then they compare that to the spectra actually coming from the spectrometer, and in that way gain an understanding of computational aspects such as how to read data in and manipulate large data arrays, plot them, etc. And also experimentally how to use the spectrometer, and of course conceptually how a clear case helium neon laser works, and why we see wavelengths other than the lasing wavelength. Another laboratory that we have been working on is a Thermocouples laboratory, where we explore the Seebeck effect and simulate that as n particles in a box, where we have applied a temperature gradient, and we use the experiment to calibrate a thermocouple. So we use known melting points of different chemical substances to calibrate the thermocouple fitted to a particular model, and then do a simulation with and particles in the box to see that indeed more particles would go to the hot side, or excuse me, to the cold side rather than the hot side for a material that has a negative Seebeck coefficient, and then the opposite for a material that has a positive Seebeck coefficient. So what our students do after each of these laboratories is publish their results using MATLAB. And so what they do is they code their laboratory reports into MATLAB using appropriate syntax so that, for example, they can put a purpose and titles in, and when they go to publish, then we get a nice report with a table of contents that is what they then hand in to be graded. So this part corresponds to the communication piece of the course, where our students have to explain in writing the work that they did and include their MATLAB scripts, plots that they use to analyze the data, and their analysis and their conclusions. One thing that we have done unique to this course is that because we have placed so much emphasis in computation and experiments, we wanted to be able to test those skills. And so rather than having tests during class time, we actually have the test during the laboratory period. This allows for longer tests, which decrease the pressure for those students who get nervous due to time pressures, but also allow us to introduce a computational or an experimental skill to be tested as well. And of course, as any teacher will tell you, if the students know that something is going to be on the test, they pay closer attention. So we test conceptual understanding and problem solving, and then we test student skills in programming and simulations and taking and analyzing data depending on in which part of the course we're at. The computational component of the test is typically an extension or a modification of one of the laboratories, such that the students are not starting from scratch, but actually have to understand what their code does and how to modify it in order to successfully complete the task that they're being evaluated on. And it is usually during this first exam that they are finally convinced of the importance of writing code that is well formatted and commented, because they will use it again in the test, and sometimes if it's not well formatted and well commented, they have a hard time figuring out what they themselves wrote. So this extended testing time is a great advantage, as it, like I said, takes the pressure off of the students, and it allows the test to become a learning opportunity as students are working on their computation and experimental skills. Now, what happens in the upper level courses? Well, between 2003 and 2006, computational models were developed for all upper level courses as part of an NSF CCLI grant that is described in the paper referenced on this slide. The modules were actually developed in MATLAB and were a good first step towards increasing the computational content in our program, but they had a weakness, and that weakness is that because we didn't have this common base where we knew that all of our students had particular skills in MATLAB, we allowed them to use different languages and basically choose whichever they were more comfortable with. So what was the problem with that? Well, what happened was that it was hard for the students to work collaboratively, so they could not really talk to each other about the specifics of the code, but it was also difficult for the instructor to provide guidance and feedback when there were different computer language being used that maybe the instructor was not as familiar with. So now that we're using MATLAB and building a solid foundation in applications of modern physics, we have started requiring all of our upper level students to use MATLAB in our upper level courses. And we've also increased the use of MATLAB by introducing homework and projects, even more than those that were developed with the NSF CCLI grant that use MATLAB. So our curriculum development goals are to take advantage of MATLAB as a common tool by embedding computation in large and small ways throughout the curriculum. And we're currently doing this focusing on these 4 courses: theoretical mechanics, E&M, optics, and quantum mechanics. And what we want to do is to connect the theory and the idealized physical systems that we present in lecture with real systems through the use of computer simulation and validation experiments. And not all of these courses have a lab. In fact, optics is the only one that does. And so the idea for the other 3 courses is to have this computer simulations and validation experiments be short enough projects that they can be done outside of class as homework, but that keep students exposed to computation and build on the skills that they have already developed. And the validation experiments are important because, again, we want students to be able to take the theory and apply it to real systems. And so we want them to see that, yes, this is in fact the way that things work. And for systems that you cannot get an analytical solution, computer simulation is really the key to translating between theory and experiment. So here are a few of the projects that we're currently working on and introducing into our upper level courses. In theoretical mechanics, we are using coupled metronomes and studying those using MATLAB as well as running the experiment. In electricity and magnetism, we are using different geometries of capacitors to understand the potential differences between the two and the electric fields in between the 2 plates. So we could do parallel plates, cylinders, and shapes that cannot be solved for analytically, but that we can get a simulation for and then test in the lab. In optics, we're concentrating on polarized light and how to better understand what is happening through the use of simulations and visualizing through plots and GUIs, and also have an experimental component there. And finally, in quantum mechanics, we are using quantum dots to explore the particle in a spherical box, both in theory, numerically, and in an experiment to use the emission spectra of these quantum dots to tie that to their size. The advantages that we have found as we've introduced MATLAB throughout our curriculum are that the students are gaining greater conceptual understanding. Doing the simulations allow us to ask more open-ended questions, which foment creative thinking and encourage collaboration between our students. And we've also found that giving our students this tool in their arsenal means that they are now better prepared to join the workforce, to go to graduate school, and see computation as just one more way of solving a problem. Now, what are the challenges? Well, having students write their own simulations is time-consuming, and so we've solved part of that problem by doing that first experiencing computational physics inside the laboratory for the applications of modern physics course. In the upper level courses, we've tried to make the projects small enough that they can be homework projects or individual projects that don't take as much of the students' time, but we still have to account for the time that students are going to spend on that. One big challenge, I believe, is that, as this quote reads, computational physics does not yield instant gratification, as is found in many other computer applications. And so it is a challenge to get students to try different things and to not get frustrated with the coding when they're just starting and don't know how to debug their code or how to test their code to see that it's actually doing what it should be doing. One challenge that other departments may face that luckily we've all agreed to at St. Thomas is the buy-in to the project. So doing MATLAB in all of our classes means that all faculty must be able to code in MATLAB and have enough experience to help the students, and so there must be buy-in from all of the faculty. And developing this expertise, of course, is time consuming for the faculty as well, and has required close collaboration between all of us as we try to develop these materials. I would like to acknowledge the University of St. Thomas Department of Physics and grants from the University of St. Thomas Faculty Development Center, the National Science Foundation, and MathWorks, all of which have supported this project. The faculty and students involved have been key to this project as well. I would like to finish the webinar by inviting you to contact me if you have any questions, and to visit the curriculum development website for applications of modern physics, which you can get to from the classroom resources page in MathWorks, or from the website that's at the bottom of this PowerPoint. What is described in there are all of the laboratories that are included in the course in much more detail, and I would be happy to send you the materials that I have if you decide that you would like to try this out in your own course.